Hey guys, my name is IBM and this is going to be lesson, I think this is lesson 4. And lesson 4 is going to be the last lesson and I think it's in dynamics, and I think it's going to be the most important lesson of dynamics, because here we are now going to look at collisions in more details. We're going to look at the different types of collisions, that is the elastic and inelastic collisions. And then that is basically what is going to be in lesson number 4. And this is the most important part of dynamics that you'll always find in the past paper questions. Okay, so let's talk about elastic and inelastic collisions. So collisions, as we have already said, in everyday life we experience collisions, and we said sometimes the bodies stick together and move as a common body, and sometimes they separate, sometimes they bounce off, sometimes they just change direction after collision, and so on and so forth. So collisions can be categorized as being elastic, or when I say elastic, I basically mean perfectly elastic. So the collisions are going to be classified as being elastic or simply perfectly elastic, and we have inelastic or perfectly inelastic collisions. So to distinguish between the two collisions, or between the collisions of bodies, we use the principle of conservation of momentum and the principle of conservation of kinetic energy, or the principle of conservation of energy. So of course we know that as long as the system is always isolated, that is no resultant forces acting, um, the momentum will always be conserved, or total momentum before the collision will always be the same as total momentum after the collision. But kinetic energy may be conserved or it may not be conserved, depending on whether the collision is elastic or inelastic. So whenever objects collide in the absence of external net forces or external resultant forces, we saw that total momentum or the net momentum never changes. In other words, the net momentum before the collision is always the same as the net momentum after the collision. Now, this is going to be true whether the collision is elastic or inelastic. As long as there is no external dissipative forces acting, total momentum before any collision will always be the same as total momentum after the collision. However, for conservation of energy, the sum of kinetic energies before collision is going to must be equal to the sum of kinetic energies after the collision. And this second condition is what is going to help us distinguish elastic collisions from inelastic collisions. So to understand elastic and inelastic collisions, we are saying in both collisions we are going to see that momentum is always conserved. But kinetic energy, conservation of kinetic energy, will help us to distinguish between elastic and inelastic collision. So one important thing we need to note is that the total momentum remains constant in any type of collision, whether it is elastic or inelastic. The total momentum is always going to be constant. However, the total momentum, total kinetic energy is generally not conserved in the collision, because some of the kinetic energy is converted to thermal energy and internal elastic potential energy, which is stored in the object. So sometimes kinetic energy is not conserved. And whenever the kinetic energy is conserved, the collision is going to be said to be elastic. So if kinetic energy is conserved after already conserving momentum, if kinetic energy is conserved, the collision is going to be elastic. And if kinetic energy is not conserved, the collision will always be inelastic. So kinetic energy or conservation of kinetic energy is always going to help us to distinguish between elastic and inelastic collision. And we are saying if the collision is elastic, kinetic energy is conserved. Of course, momentum has already been conserved. But if the collision is inelastic, kinetic energy is not going to be conserved. So if the collision is elastic, kinetic energy will be conserved. In other words, total kinetic energy before any collision will be the same as total kinetic energy after the collision. If the collision is inelastic, kinetic energy is not going to be conserved. In other words, total kinetic energy before the collision is always greater than total kinetic energy after the collision if the collision is inelastic. So the collisions are going to be classified as elastic and inelastic, and we are saying for elastic collision, kinetic energy is going to be conserved. Let's first concentrate on elastic collisions or perfectly elastic. Many times I will just say elastic, but it's always perfectly elastic. So this is going to be the type of collision where linear momentum is conserved and total kinetic energy is conserved, and the bodies normally separate after the collision. So many times for perfectly elastic collision, the bodies must separate after the collision because if they stick together, by all means, kinetic energy is going to be lost. If they stick together, the kinetic energy is going to be most likely going to be lost. So they normally separate after the collision. So the elastic collisions can either be in one dimension, that is in one straight line, or they are going to be in one dimension, in one straight line, or in two dimensions. So one dimension will be head on, that is in a perfect straight line, and they continue moving in a perfect straight line. And then we have what we call non-head on, that is in two dimensions. They may be in the same horizontal plane but move in the y and z or y and x direction after the collision. So what we call a head-on collision is that elastic collision in which the colliding bodies move along the same straight line before and after collision. That's what we are going to call head-on. The bodies were initially moving in a straight line, and even after collision, they continue in a straight line, in the same straight line after the collision. That's what we call head-on collision. That is going to be one dimension, and that is what you consider in IGCSE. Then we shall later on see two dimensions or non-head-on collision. So during elastic collision, the bodies will be deformed at the region of contact. Of course, at the region of contact, when they deform, energy is stored in the form of elastic potential energy and which when they undeform, the energy is converted back into kinetic energy to move the bodies after the collision. So part of the kinetic energy will be converted into elastic potential energy. The bodies will regain their original shape due to elasticity, and then the potential energy will be reconverted back into kinetic energy to again move the bodies after the collision, to give the bodies velocities after the collision. So that is during elastic collision. Head on, the bodies are initially in a straight line, and even after collision, they continue moving in a straight line. A simple illustration of elastic head-on collision can be this one here. So we have two bodies, M1 and M2, moving in a straight line, even though they are moving towards each other. So before collision, M1 is moving towards the right with the speed u1, and M2 is moving towards the left with the speed u2. They are moving in a straight line. So after collision, again, they continue moving in a straight line, only that M1 moves to the left and M2 moves to the right. Such collisions are considered to be head-on collisions. They move in a straight line after collision. So what we are supposed to do is we're going to conserve both momentum, or to check conservation of momentum and conservation of kinetic energy in both cases. So to begin with, by conservation of momentum, remember velocity is a vector quantity and we prefer to give velocities to the left, to the right positive and velocities to the left negative. So the momentum of this one before collision is m1 u1. The momentum of this one before collision is m2 u2, but it's going to be negative because it's in the opposite direction. Then we shall sum up to find the total. The momentum of m1 after collision is going to be m1 v1, but because it is on to the left, it will be negative. Then we shall sum this up to the momentum of m2 after collision is m2 times v2. So by conservation of momentum, we know that the total momentum before collision must be equal to total momentum after collision. So if we assume that m1 and m2 are equal and just equal to m, so if we assume that m1, m2 are equal and let them just be equal to m, so it means m1 and m2 cancel out. So in that case, I only remain with u1 minus u2 equals negative v1 plus v2, and I will call that one equation number 1. So I have considered conservation of momentum. Then I'll consider the second condition because remember this collision is elastic. Both momentum and kinetic energy must be conserved. And remember for kinetic energy is equal to half mv squared. So by conservation of kinetic energy, total kinetic energy before collision is equal to total kinetic energy after collision. You will notice that when I'm calculating the energy, I don't put a minus on the velocities. I don't subtract the kinetic energies because energy is a scalar quantity. So I get the kinetic energy of m1 is a half m1u1 squared plus the kinetic energy of m2 is a half m2u2 squared without subtracting because kinetic energy is a scalar quantity. I can't subtract the kinetic energy here. I just find the sum. So remember I have assumed that m1, m2 are equal and they're just equal to m, so m cancels out. And in that case, if m cancels out, I simply remain with the u1 squared plus u2 squared equals to v1 squared plus v2 squared. So I'm just going to rearrange and I'm just going to rearrange this. So this is I'm going to just rearrange this so that I'll take v1 to the other side and I take u2 to the other side so that I have an equation similar to this. So u1 squared minus v1 squared equals to v2 squared minus u2 squared. I'm just rearranging this equation. So now I have a difference of two squares where u1 squared minus u2 squared is the same as u1 minus v1 into brackets u1 plus v1. Then I have on the right hand side I have v2 minus u2 into brackets v2 plus v1. That is the difference of two squares. So this is the difference of two squares. So this will be therefore u1 minus v1 into u1 plus v1 equals to v2 minus u2 into v2 plus u2. So I'm now going to combine the first equation with the second equation. So I can rearrange the first equation. So that the first equation now becomes u1 plus v1 equals to the left hand side I have v2 plus u2. So I have this and the first equation as u1 plus v1 equals to v2 plus u2. So if I combine, I'm going to replace u1 plus v1 with u2 plus v2 so that this equation can be simplified further. So I will have where there is u1 plus v1, I'm going to put v2 plus u2 so that this becomes u1 minus v1 into brackets. Where there is u1 plus v1, I'm putting there u2 plus v2, which is equal to v2 minus u2 into v2 plus u2. So this is the same as that, so they cancel out. So I remain with u1 minus v1 being equal to v2 minus u2. So when I rearrange this, it gives me u1. Bring the u's on one side, I have u1 minus or plus u2. Bring the v's on the same side, the other side I have v2 plus v1 or v1 plus v2. Okay, so it means I'm arriving at u1 plus u2 and v1 plus v2. And if you come back here on the diagram, u1 plus u2 is the same as u1 minus negative u2 because this was positive, this was negative. So it means this gives us u1 plus u2. And coming back here, this was negative, this is positive. So this is the same as v2 minus negative v1, which is the same as v2 plus v1. Because v2 was to the right hand side and v1 was to the left hand side. So it's like this is going to be called the relative speed. The word relative means a difference between two speeds, difference between two quantities. Relative speed of approach is the same as the relative speed of separation. So when we combine the two equations, equation 1 and equation 2, we come up with the fact that relative speed of approach is equal to the relative speed of separation. That is for an elastic collision. So combining the two equations, I've come up with a situation that the relative speed of approach is equal to the relative speed of separation, and you should be able to derive that simple equation. Relative speed of approach is equal to the relative speed of separation. So this is a perfectly elastic collision. We say that the relative speed of approach, that is when the difference between the speeds when the objects are coming together, putting in mind the direction, as opposite direction should be negative, should be equal to the relative speed of separation. This relation is useful only for a perfectly elastic collision. So for a perfectly elastic collision, sometimes you may not know the masses, but you know the speeds towards each other and after the collision. So in that case, you just consider the simple relation that the relative speed of approach should be equal to the relative speed of separation for a perfectly elastic collision. Okay, so I'm going to show this. Here I have considered two bodies moving towards each other. I'm going to show another example and see if I can arrive at the same thing, relative speed of approach being equal to the relative speed of separation, even when the directions have been reversed, before we continue any further. Okay, so we have non-head-on collision, but before we go to non-head-on collision, I want to show people that the relative speed of approach is equal to the relative speed of separation every time. So we are going to consider a simple situation, a different situation where the two objects were initially moving, let's say, in the same direction. Let's say this is moving to the left, to the right, and this is moving to the right. Let this be U1 and this is going to be U2. That is before collision. And after collision, let's say one of them rebounds. Let's say one of them rebounds. This is going to be V1. And of course, both of them cannot rebound. The other one should continue on its direction. Let this be V2. I'm just going to consider them having an identical mass m for easy understanding of what I mean by relative speed of approach and relative speed of separation. To begin with, I'm going to conserve momentum. Remember, velocities to the left, I'm going to take them to be right to be positive, and velocities to the right, I'm going to take them to be negative. So by conservation of momentum, total momentum before collision is going to be m times u1 plus m times u2, because they are all to the right hand side. This should be equal to total momentum after collision. Remember, for v1 it is to the left hand side, so this is going to be negative m v1 plus m v2. So m cancels out. In that case, m cancels out. So I have that u1, I'm collecting like terms, so v1, I'm bringing the ones to on one side, so I have u1 plus v1 is equal to, the other side I have v2 minus u2. So here I have conserved momentum. Now I'm going to conserve kinetic energy. Total kinetic energy before, remember you don't use a minus when you're dealing with the kinetic energy. Total kinetic energy before is a half m mu1 squared plus a half m u2 squared. That is before collision. Then after collision it is a half m v1 squared plus a half m v2 squared. So m cancels out because it is a common factor. A half also cancels out because it is a common factor. So you remain with u1 squared plus u2 squared equals to v1 squared plus v2 squared. So I just bring the ones on one side so that I have u1 squared minus v1 squared. The other side I have v2 squared minus u2 squared. These are difference of two squares. So this becomes u1 minus v1 into u1 plus v1 should be equal to v2 minus u2 into v2 plus u2. So we notice that u1 plus v1 is the same as v2 minus u2 from the first equation. So where there is u1 plus v1, I'm going to put there v2 minus u2. So this equation now becomes u1 minus v1. Where there is u1 plus v1, I'm going to put there v2 minus u2. So this is going to be equal to v2 minus u2 into v2 plus u2. So v2 minus u2 has cancelled out. So I remain with the u1 minus v1 being equal to v2 plus u2. Now I'm going again to bring back the u's together. So I have u1 minus u2 on one side should be equal to v2 minus or plus. It becomes plus because this is a negative. When it goes the other side, it becomes plus v2. Now let's look at this. What is u1 minus u2? It is the difference between the velocity of the first object, the first mass, whose velocity was u1, minus the second mass, whose velocity was u2. Why is there a minus this time? It's only because both of them were positive. So when we subtract, there's a minus there. Both of them were in the same direction. So this is the relative speed of approach. u1 must be bigger than u2 if these two are supposed to meet and collide. Then let's also examine this one here. So this is v2 plus u2, not v2 plus v2. So let's look at, let me see this, what have I left out here? I took u to the other side, so this is v1, not v2. Let's look at v2 plus v1. Note that v2 was to the right hand side, so it is positive, and v1 was to the left hand side, so the relative speed would be v2 minus negative v1, which is the same as v2 plus v1. So that means this is going to be the relative speed of approach, and this is called the relative speed of separation. So for an elastic collision, the relative speed of approach is the same as the relative speed of separation. For more understanding and confidence in this, I ask you to visit the solved past paper questions, where you'll find such questions which require relative speed of approach and the relative speed of separation. Okay, so let's now talk about a non-head-on collision. Non-head-on collision. What do we mean by non-head-on collision? Unlike head-on collision where the bodies were moving in a straight line, and even after the collision, they continued to move in a straight line. So for non-head-on collision, this is what you always observe when you are playing this kind of game every day. The collisions do not necessarily need to be in a perfect straight line. So for example, in this animation here, you might have seen that if you want to target a ball to any of these holes, you must use some skill so that you slice the ball so that it can move towards the hole you want. So you can't make the motion cannot be in a perfect straight line if you want to uh, to cause the ball to move in a certain direction. For example, in shooting the ball which was here using the white ball, you have noticed that the ball which was initially here was directed here by shooting using a white ball, but the white ball had to take the other path. So we now have two directions here. We have this direction where the other ball took to go towards the hole, and we have the other direction where the white ball which we used to shoot moved. So that kind of motion is called non head-on collision, because two dimensions or two motion in more than one direction or motion in more than one dimension is involved here. So such collisions are going to be very common, and we are going to call them non-head-on collision. And if you're good at playing this game, you must have noticed that sometimes you try to calculate how much you should hit the ball and at what point you should exactly hit the white ball, so that, or at what point should the white ball hit the one you want to target into the hole. So by using that concept, you are actually using the principles of collisions, and that is basically non-head-on collision. So we can have non-head-on collision which is also elastic. So suppose that an object of mass, say m1, moving with initial speed, say u1, strikes a second object of mass m2, which is at rest. So m2 is initial at rest, and m1 is now our white ball, which is going to hit m2, which is initial at rest. And since the collision is elastic, so it means momentum must be conserved as before, and also we must ensure that kinetic energy is also conserved. Unfortunately, this kind of motion is not in one dimension, so we must consider two dimensions at two different instants. So because this is both in the horizontal and the vertical, so we must consider momentum parallel to the initial direction of motion and perpendicular to the initial direction of motion. So you must consider the momentum after collision parallel or along the initial direction of motion and perpendicular to the initial direction of motion, that is in the vertical, as shown in this, with these arrows. So in this case, we must find x and y components of momentum. And of course, by conservation of momentum, the total momentum in the x must remain constant, and total momentum in the y must also remain constant. In other words, total momentum in the horizontal before the collision must be equal to total momentum in the horizontal after the collision. Also, total momentum in the vertical before the collision will be equal to total momentum in the vertical after collision. But I want you to notice that the mass which is causing the motion after collision was only moving in the horizontal, which means the vertical component in momentum before collision was 0. But then after the collision, the m2 has a component of velocity in the vertical, which would be v2. When I resolve cos theta, when I resolve theta 2 to the vertical, to be when I resolve v2 to the vertical, to be v2 cos of theta 2 upwards. So the component of m in the m2 in the vertical upwards will be v2 cos theta m2 upwards. And then for m1, the component of m1 in the vertical will be v1 cos, not cos, this is sine, because it is in the vertical. So this will be v2 sine of theta 2, and this will be v1 sine of theta 1 in the vertical. Of course, in the horizontal, we resolve v2 to the horizontal will be v2 cos of theta 2, and will point to the left hand side, to the right hand side. v1 to the horizontal will be v1 cos of theta 1, and will also point to the left, to the right hand side. So it's like v1 cos theta points, and v2 cos theta both point towards the right. So we must consider momentum before the collision and momentum after the collision. So if we do that, therefore, we must consider the x and y components of the total momentum. So momentum conservation in the horizontal, in the x direction. Initially, m1 was moving the speed u1, m2 was not moving. So total momentum before collision is going to be m1 u1 plus 0, because for m2 it was initially 0. But after collision in the horizontal, or in the x direction, or along the original direction, it will be m1 v1 cos theta 1, that is the velocity in the horizontal after collision, plus m2 v2 cos theta 2, that is the velocity of m2 in the horizontal after collision, times m2. We are adding because these are just going to be in the same direction, so we sum them up in that direction. Then we have to conserve momentum in the y direction, or in the vertical, after the collision. So initially, the body which caused the motion, or which caused the collision, was moving in the horizontal. So it means initial momentum in the vertical is automatically 0. None of the masses was initially moving in the vertical before collision. So the momentum in the vertical before collision is 0. But after collision, M2 moves upwards and M1 moves downwards. So they're in opposite directions. Therefore, one of them must be negative. So I can say downwards is negative and upwards is positive. That's why I have 0 equaling to negative M1 V1 sine theta 1 plus M2 V2 sine theta 2. And of course, this gives us M1 V1 sine theta 1 equals M2 V2 sine theta 2. So you'll be finding such questions in paper 2, most likely, when you need to resolve, or even in multiple choice questions. However, just consider momentum in the horizontal independently. Total momentum before should be equal to total momentum after. Then consider momentum in the vertical independently, and total momentum before was 0, should be equal to total momentum after. But because one is upwards, one is downwards, they will be in opposite directions. But when it comes to conservation of energy, we don't consider resolved values of velocity. Total kinetic energy before collision should be equal to total kinetic energy after collision, but I am saying we do not consider the resolved values of velocity because kinetic energy is a scalar quantity. It doesn't depend on the direction of the velocity. Kinetic energy is a scalar quantity. It will not depend on the direction of the velocities. Okay. So for collisions in two dimensions, therefore, we should always be able to consider resolving these both in the vertical and the horizontal. And if you wanted to get a vector diagram to show or to obtain the final momentum, you can still do that. If this takes this path, for example, x takes that path, and y takes this path. So it means the momentum for x is going to be along this direction. So the momentum for y is taking this direction. So I have to join these two. The initial momentum was this one here. The initial momentum was in the horizontal. Then the final momentum for x is along this direction. And the final momentum for y, of course, I have to join this head to tail. Because remember, total momentum must always be conserved. So it means I'll have a vector triangle which looks like this. The initial momentum was in the horizontal. Then the final momentum for x takes that path. Then the final momentum for y is in this path. So I can come up with a vector triangle using the three momentum. Initial momentum, final momentum for x, and final momentum for y. And it means that the total of these two should be equal the same as the initial momentum. The final momentum of x combined with the final momentum of y should give us the initial momentum of x. And you can notice that when we join these two head to tail, they form this kind of loop, which is a clockwise loop. And the initial momentum is the other way around, which means total momentum before collision is equal to total momentum after collision. However, I said you can resolve this, consider momentum in the x direction or in the horizontal direction. And if the mass of this is mx, the mass of y is my, so you will say total momentum before collision is mx times u plus, assuming y was initial at rest, so that will be plus 0. Should be equal to total momentum after collision. I have to resolve x in the horizontal. This will be vx cos of theta x. And for y, that will be vy cos of theta y, and they will point in the same direction. So this will be equal to mx times vx cos of theta x plus my times vy cos of theta y. That is in the x direction. So you have also to consider the y direction, which is in the vertical. In the vertical, initially there was no motion in the vertical, so total momentum in the vertical is 0. But then resolving this in the vertical, x will go upwards, whose velocity will be vx sine of theta x, and y will go downwards, whose velocity will be vy sine of theta y. So this will be equal to negative mx Vx sine of theta x plus my Vy sine of theta of y. So I've made one negative, one is positive, which also implies that mx Vx sine of theta x is the same as my Vy sine of theta y. So you can just resolve this, but it's the same as drawing a vector triangle, because we know that total momentum before should be equal to total momentum after if the collision is elastic, and of course total energy, total kinetic energy before is the same as total kinetic energy after if the collision is elastic. So I fix the total initial momentum. Then on the total initial momentum, I add this vector for x and the other one for y. And the sum of x and y should be equal to the initial momentum of x, because initially it is only x which had momentum. So you should also be able to draw this kind of vector triangle for the three vectors. Okay, we shall come back to that when we do examples. Let's talk about inelastic collision. So like for elastic collision, we have also said momentum is conserved for both elastic and inelastic collision, only that for inelastic, kinetic energy is not conserved. For inelastic, kinetic energy is not conserved. Some of the energy changes to heat or sound, which are not recoverable, and they may not really be very useful for any other purposes after the collision has occurred. So sometimes the particles stick together, that is, they coalesce and move with a common velocity. So it becomes a conjoined body sometimes. That is what we shall call a perfectly inelastic collision. So an inelastic collision in which the two sliding objects or two colliding objects stick together and move as a single body after collision may be called perfectly elastic. I mean perfectly inelastic. But doesn't mean that it is only when bodies combine that is when we have that's when we have inelastic collision. No, even when they bounce off each other and they don't stick together, we can still have inelastic collisions as long as kinetic energy is not conserved. So for an inelastic collision, momentum is conserved, but kinetic energy is not conserved. That's what we call inelastic collision. But I've said if the collision is such that the bodies collide and stick together after the collision, such a collision can be termed to be perfectly elastic, inelastic collision. For example, we have two masses m1 and m2. m1 has speed u1 and m2 has speed u2. They collide, and after collision they become one body. So that means they move with a common velocity v. So this is what we call perfectly inelastic. Of course, for such a collision, only momentum must be conserved, but not kinetic energy. So total momentum before collision is m1u1 plus m2u2 because they're in the same direction, so velocities to the right can be positive. And after collision, they stick together, so it becomes one mass, which is m1 plus m2, then times a common velocity. That's what we call perfectly inelastic. So an inelastic collision can also be non-head-on, that is, it can be at an angle. So as long as kinetic energy is not conserved, as we are going to see, an inelastic collision can also be non-head-on collision. Okay, let me also talk about momentum conservation in explosions, such as during maybe atomic bombs or any other small explosions. So let's consider a simple illustration here. Let's say we have a particle which is a single particle as shown in this case, and after an explosion, several other particles or fragments from the particle move further apart. Before explosion here, the momentum is zero. And after explosion, total momentum should also be zero. That means these particles, these fragments are going to move in several directions so that when we sum up the momenta of each of these, total momentum will be zero because total momentum must be conserved. These fragments cannot move in one direction because if they all move in one direction, then that means total momentum after the explosion will not be zero. And that means the law of conservation of momentum or the principle of conservation of momentum would be violated in that case. So these fragments after the explosion must move in opposite several different directions so that when we sum up, for example, the momentum of this could cancel out this one. The momentum of maybe this could cancel out the other momentum and so on and so forth. So that means total momentum would be zero as before. So after the explosion, the individual parts of the system, that is often a collection of fragments from the original object, have momentum. And if the vector sum of all individual parts of the system could be added together to determine total momentum after the explosion, then it should be the same as total momentum before the explosion. So this means our momentum is going to be conserved even after an explosion. Total momentum before the explosion was zero, so we expect that total momentum after the explosion should still remain zero because momentum is always conserved as long as the system is an isolated system. In summary, if the collision is elastic, total kinetic energy before collision is equal to total kinetic energy after collision. In simple terms, kinetic energy is conserved. So collisions in which total kinetic energy is not conserved is not the same before and after the event. We shall call them inelastic. So every time you verify, or if you can verify that kinetic energy is not conserved, then you are free to conclude that the collision is inelastic. However, the majority of collisions in everyday life are not elastic in nature. They're actually inelastic because in most cases, a large fraction of kinetic energy is always wasted. Some fraction of the initial kinetic energy of the collision of the colliding objects is usually converted into some other form such as heat, normal, or energy associated with the mechanical deformation of the objects during the collision. So many times after collision, energy is wasted as heat. Therefore, most of the collisions in nature are actually inelastic. They are not elastic. Although kinetic energy may or may not be conserved in a collision, as long as the system is isolated, we said momentum is always conserved in any isolated system. That's why we have the principle of conservation of momentum. As long as the system is isolated, that is, there are no dissipative forces acting, the total momentum before is always equal to total momentum after. In other words, total momentum is always constant. So, total energy is always conserved. The law of conservation of energy is not violated. Even though kinetic energy may not be conserved, total energy is always conserved. What do I mean by that? Kinetic energy is just converted, some of it is just converted as heat, but if we sum up the remaining kinetic energy plus what has been converted into heat, total energy before is always going to be conserved. So the total energy is always conserved, even though kinetic energy may not be conserved because it is just converted into other forms. Total energy is always conserved. So energy is neither created nor destroyed, but is simply transformed from one form to another. So during an inelastic collision, part of the kinetic energy is transformed into heat. It doesn't mean that energy has been lost. It has just been given or it has just spread into less useful forms. So total energy is still conserved, even though it is less the heat form is less useful. So the law of conservation of energy is not violated, but kinetic energy is not conserved. Okay. So I want us to do a few examples using the concepts that we have just been exploring about elastic and inelastic collisions. Example number one, two bodies of mass 3 kilograms and 5 kilograms traveling in opposite directions on a horizontal surface collide. The velocities of the 3 kilogram and 5 kilogram bodies before collision are 6, So 3 kilograms 6, 5 kilograms 5 meters per second, respectively. They separate after collision and move in the same direction. So they separate after collision and move in the same direction in which the 5 kilogram body mass was moving before collision. Given that the velocity of the 5 kilogram body after the collision is 1 meter per second, find the speed of 3 kilogram body after impact and the percentage loss in energy, if at all it is there. Okay, so I may want to sketch this, but even though, of course, in an exam, the diagrams are already sketched. So we have 3 kilograms and 5 kilograms. So this is 3, 5 kilograms. So this was moving 6 meters per second, and this was moving towards each other because they were traveling in opposite directions. So they can't be moving away from each other. That means they will not collide. So they must be moving towards each other in opposite directions, that is towards each other. So let this be 5 meters per second. So after collision, we have after collision, they separate after collision and move in the same direction in which the 5 kilogram body was moving. So it was moving to the left. So let the speed of this be v for 3 kilograms, and let this be 1 meter per second. 1 meter per second for the 5 kilograms. Okay, I didn't want to sketch this. So this is before and this is after. So given the velocity of the 5 kilogram body after collision is 1 meter per second, find the speed of the 3 kilogram body after the collision. Okay, so we are just going to use conservation of momentum and then conservation of kinetic energy. I'll change the color of the pen. So by conservation of momentum, or from conservation of momentum, total momentum before collision should be equal to total momentum after collision. Remember, momentum is mass times velocity. Always write a formula somewhere. So for total momentum before collision, I'm going to consider velocities to the left negative, velocities to the right positive. So we shall have 3 times 6, that is positive, plus velocities to the right negative. So this would be negative 5 times 5. So this is total momentum before collision, should be equal to total momentum after collision. Remember, velocities to the left negative, so this would be negative 3 times v plus negative 5 times 1. Velocities to the left negative. So I have that 18 minus 25 equals to minus 3v minus 5. So this gives us a negative, I'm collecting like terms, 18 minus 25 plus 5. So this is negative 2 equals to negative 3v. So v is going to be 2 over 3. So v is 2 over 3 meters per second. Oh, this is 0.67 meters per second. Equals to 0.666 recurring up to 7. Okay, so that is the speed of the 3 kilogram mass, that is 0.67 meters per second. I've used the conservation of momentum. Then to find the loss in energy, I have to find kinetic energy before collision. I'll call it E1. Total kinetic energy before collision is going to be, remember, I don't consider the signs of the direction of the velocity for kinetic energy. So it will be a half times the mass, which is 3 times 6 squared, plus a half times the mass, which is 5 times 5 squared. That is total kinetic energy before collision. So I'll check with my calculator. 0.5 times 6 squared times 3 plus 0.5 times 5 times 5 squared. So this is 116.5 joules. Many times students forget to square when it comes to kinetic energy. Then let me find kinetic energy after the collision, I'll call it E2. So this will be a half times the 3 times the speed after the collision, which is 3 squared, plus a half times 5 times 1 squared. The speed after the collision is 2 over 3, not 3 squared. 2 over 3 squared, that was V. So I'll check my calculator here. So this gives me 3.2 joules. So the difference in energy, or what it would be like the loss in energy, but remember we said energy is not completely lost, it's just transformed to other forms which are not kinetic. So the difference in kinetic energy is going to be 116.5 minus 3.2, which is, that is 113.3 joules. Then the percentage loss is going to be 113.3 divided by 116.5 times 100. Which is approximately 97% as required. So I think that is a good example using conservation of momentum and then conservation of kinetic energy. So this collision cannot be elastic, but whether elastic or inelastic, kinetic energy, momentum is always conserved. Another example, this is in 2 dimensions. An alpha particle A of mass 4 units is incident with a velocity V on a stationary helium nucleus B. So B is stationary. After collision, A moves in direction BC with a velocity V over 2, where BC makes an angle 60. The helium nucleus moves along BD. Calculate the velocity of rebound of helium nucleus along BD and the angle it makes with the direction AB. So we shall start with conservation of momentum. Remember, you have to consider both the horizontal and the vertical. So let me start from here. So we are going to consider x direction. That is in the horizontal direction. First, A was moving. A has a mass of 4 units. And B also has a mass of 4 units, so they have the same mass. So in the x direction, total momentum before collision is going to be 4 units times V. The other one is at rest, so it is 0 plus 0. Should be equal to, I have to resolve V2 in the horizontal. V over 2 in the horizontal will be V over 2 cos of 60. And then I also have for the helium in the horizontal it is going to be, let's say, I'm going to say for helium, let it be, which letter should I use here? Okay, let me use X for helium. So for helium, it is going to be X cos of theta. That is its velocity in the horizontal, which points to the right-hand side. So momentum after collision is going to be for B. B takes the path BD, so this is going to be X. The mass is 4 units times X cos of theta plus, for A, it takes the line BC, so in the horizontal it is going to be 4 units times V over 2 cos of 60. Okay, so we can try to simplify this where possible. I think cos of 60 is half. cos of 60 is a half. So this is the same as 4 has already cancelled out. The 4 cancels out because it's a common factor. So we have that V is equal to cos of theta x cos of theta. We know that cos of 60 is a half, so this becomes plus V divided by 4. Alternatively, I can say 4 for V minus V is equal to x cos of theta, just collecting like terms. So I'll have that 4V minus V. So that becomes 3V equals to x cos of theta. So that is going to be one of the equations I'm going to consider. Let's also consider, no, I didn't multiply 4 here. Sorry for that mathematics. There's a 4 here. If I multiply everything by 4, I have that 4V equals to 4x cos theta plus V. So this becomes a 3V equals to 4x cos of theta. Or I can say that cos of theta equals 3V over 4 of x. Okay, so this is going to be one of the equations. Then I'm going to consider in the y direction or in the vertical direction. In the vertical direction or in the y direction. Initially, all of them, it is only A which was moving, and it was moving in the horizontal. So total momentum in the horizontal is 0 initially. Then total momentum after, so I have to resolve the velocities. One will be downwards here. X in the horizontal will be x sine of theta. The mass, remember, is 4 units. Then V over 2 in the vertical is going to be V over 2 sine of 60. So the momentum, one of them will be positive, one will be negative. So this will be 4 units times the velocity, which is V over 2 sine of 60 upwards, plus negative downwards. It is going to be 4 units times x sine of theta. So that means 4 cancels out. And I have that x sine theta is equal to V over 2 sine of 60. But I think sine of 60 is root 3 over 2. So I can say that x sine theta is equal to V root 3 over 2. If you're not sure, you can press your calculator. V root 3 over 2. Or this becomes 4. Because sine 60 is root 3 over 2, then times the 2 in the denominator, that becomes 4. So I have that sine of theta is equal to is equal to V root 3 divided by 4x. So this is going to be my second equation. This is my first equation. So I'm going to divide the two equations. So I have that sine of theta divided by cos of theta is equal to, so I have V root 3 divided by 4x times the reciprocal, which is 4x divided by 3V. So this becomes root 3 over 3. I think root 3 over 3 is the same as root 3 over 3 is most likely going to be 30 degrees, I think. Root 3 divided by 3, shift, tan. So it means theta is equal to 30 degrees. Whichever method you use to solve those two equations, I just want to show you the equations. Of course, the questions may not be as complex as these, apart from those doing mechanics in mathematics. Or you could use the concepts of cos squared theta plus sine squared theta equals to 1 to find whatever you want. So I have theta. Then they wanted us to calculate the velocity of rebound of helium nucleus and the angle it makes with the direction. So I now know theta is 30 degrees. So I can find x. Of course, that one I just choose any equation and I substitute. Because they want the answer in terms of v, so I'll use maybe I'll use the equation sine theta. So x is going to be equal to v root 3 divided by 4 sine of theta. So x is going to be v root 3 divided by 4 times sine of 30. And sine of 30 is a half. So this becomes v root 3 divided by 4 times a half. So x becomes root 3 times v root 3 divided by 2, or which is the same as root 3 over 2 times v. So that is x. Root 3 over 2 times v, that is x. Okay, so this was just a general question just to make you very, very confident with using angles and so on and so forth. Although it might be a little bit more complex, especially for students who are not doing mathematics. Example 3, a bullet of mass 300 grams traveling at a speed of 80 meters per second. So this is 0.3 kilograms if you want. Traveling at 80 meters per second hits a body of mass 450 grams. So this is 0.45 kilograms. Moving in the same direction as the bullet at 1.5 meters per second. The bullet and the body move together after collision. So they move together as a single body. Find the loss in kinetic energy. Okay, so we use conservation of momentum because the bullet is traveling at a speed of 8 and he's hitting another one which is moving in the same direction. The bullet and the body move together after the collision. Find the loss in kinetic energy. So first of all, I need to find the velocity with which they move after the collision. So total momentum before collision, remember momentum is mass times velocity, so they were moving in the same direction, so both velocities are in the same direction. Let's say positive. So we have 0.3 times 8, that is momentum for 300 kilograms, plus 0.45 times 1.5, that's momentum for 450 grams, should be equal to, they become one body. So their mass will become 0.3 plus 0.45. And then they move with the common velocity v. So I want to find v. I'll just press my calculator to find v. So 0.3 times 8 plus 0.45 times 1.5. Then I divide this by 0.3 plus 0.45. So the velocity after collision is 4.1 meters per second. Then I want to find the loss in kinetic energy. So I'll first find the initial kinetic energy will be a half times 0.3 times 8 squared plus a half times 0.45 times 1.5 squared, which will be 0.5 times 0.3 times 8 squared plus 0.5 times 0.45 times 1.5 squared. So this is 10.1 joules. Then kinetic energy after the collision is going to be a half into the total mass, which is 0.3 plus 0.45, then times v squared, which is times 4.1 squared. So 0.5 into 0.3 plus 0.45 times 4.1 squared. So this is equal to 6.30 joules after the collision. So the loss in energy is going to be the difference in these two, 10.1 minus 6.30. So 10.1 minus, so this is approximately 3.8. Two balls P and Q traveling the same line in opposite directions with speeds 6 meters per second, 15 meters per second respectively make a perfect inelastic collision. So it means they stick together. If the masses of P and Q are 8 kilograms and 5 kilograms respectively, find the final velocity of P and the change in kinetic energy. So I'll just sketch this for you, and then you should be able to find out if these answers are correct. So they are traveling in the same line in opposite directions. So if they collide, they must be moving towards each other. So let's see this be P, let this be Q. So let this be 6 meters per second, and let this be 15 meters per second. That is before. Then after, because it is a perfectly elastic, we expect that we expect that they stick together. So this is P plus Q. So they move with a common velocity v. I don't know which direction, but you can be able to find v. So you use conservation of momentum to find v. Perfectly inelastic collision. If the masses of P and Q are 8 kilograms and 5 kilograms respectively, find the final velocity of P. Of course, the velocity is going to be the same because they're going to move as a common body if the collision is perfectly inelastic. So we expect them to stick together. Then you should, of course, the velocity of P will be the same as the velocity of Q. Then you should find the final kinetic energy using conservation of kinetic energy, total kinetic energy before. You find total kinetic energy before collision, then total kinetic energy after collision using the common velocity, and then you subtract. You should be able to verify and see if these answers are correct. A car of mass are 1,000 kilograms traveling at a uniform velocity of 20 meters per second collides perfectly inelastically with a stationary car of mass 1,500 kilograms. Calculate the loss in kinetic energy. I will also not solve this. I'll just give you a hint. So let's say this is the first car and we have another one. So this is 1,000 kilograms. This is 1,500 kilograms. So this is moving with a velocity of 20 meters per second, and this one velocity is equal to 0. It is at rest. So this is before. Then after the collision, it is a perfectly inelastic, so we expect that they stick together. I'm just using this for simplicity. I wouldn't want to draw cars. So total mass is going to be 1,000 plus 1,500. So they move with a common velocity v. So by conservation of momentum, you should be able to find v. Total momentum before should be equal to total momentum after. You find v. Then you find the kinetic energy before collision, kinetic energy after the collision. I'll just press my calculator and write there the answers without showing the working. So I have 1,000. So I expect your value of v to be equal to 8 meters per second. Then kinetic energy. So I expect that the loss in kinetic energy to be about, I think it is around 120,000 joules. You can verify that. An object X of mass m moving with a velocity v with a velocity of 10 meters per second collides with a stationary object y of equal mass. After collision, X moves with the speed u at an angle of 30 degrees to its initial direction, while y moves with the speed v at an angle of 90 degrees to the new direction of x. Capture the speeds u and v. So this one, I will think I will solve this one. So I will try to sketch a diagram for simplicity. Let us assume that initially x is the one which is moving with a speed of 10. Yeah, this is 10 meters per second, and it collides with y, which is at rest. Then after collision, let's say this was before. Then after collision, we have something like initial direction is this one. So x takes that path, and let's say y takes this path. So this is for y. This angle, the angle between x and y is 90, at an angle of 90 degrees to the new direction of x. So this angle is 90. But x is at an angle of 30 degrees. So that means this angle is going to be 60 degrees. Okay. So we are going to conserve momentum in the horizontal direction. So x, let me say horizontal direction. I'm going to conserve momentum in the horizontal direction. So the mass, let's say the mass is m times the velocity, which is 10 for x. Of course, the other one was at rest. Its mass was m times its velocity, which is 0. In the horizontal, we have to resolve x, the speed for x after the collision. X is u, and y is given a speed of v. So we have to resolve x in the horizontal to be u in the horizontal will be u cos 30, and v in the horizontal will be v cos 60. So we have u, the mass is m times u cos of 30 plus the mass is m because they have the same mass times v cos of 60. So 10m is equal to m times, that is mu cos 60 is root 3 over 2, cos 30 plus mv, cos of 60 is a half, so this is mv over 2. So m has cancelled. I multiply everything by 2. I have that 20 is equal to u root of 3 plus v. I'll leave this as one equation maybe. Then I'm going to consider vertical momentum in the vertical. So vertical direction. If I consider vertical direction, none of them was initially moving in the horizontal, so I'll say 0 equals 2. So I have to resolve x to the vertical. Its velocity to the vertical will be u sine of 30. So the momentum will be m times u sine of 30 plus a negative because the other one will be downwards. So it will be m. Its velocity is v sine of 60. V sine of 60. So in other words, m cancels out, and I have that u sine of 30 is equal to v sine of 60. U sine 30 equals to v sine of 60. So I can simplify this again, and maybe I say sine of 30 is a half, so I say u over 2 equals to v root 3 over 2, because I know that sine of 60 is root 3 over 2. Okay, so I have I therefore have that u is equal to v root of 3. So I can substitute for u. So from the first equation, I have that 20 equals to where there is u, I'm putting there v root 3, again times root 3, then plus v. Root 3 times root 3, I think that is 3, so 20 is going to be 4v, which I think makes v to be equal to 5 meters per second, which makes u to be equal to 5 root of 3. 5 root 3 is about 5 root 3. This is about 8.7. Then determine whether the collision is elastic or inelastic. So I have to find total kinetic energy before collision. So this was part A. Part B, I'll find E1, which is going to be total kinetic energy before collision, which is a half times m times the velocity was 10, so I'll say times 10 squared. The other one was 0. I think this is 50 times m joules. 50 m joules. I don't want it to appear as if it is millijoules. It is 50 times m joules. Then I'll find E2 as the kinetic energy after the collision, which will be a half. We don't consider resolved velocities, remember. So we don't say this cos this, no. So this is going to be a half times m. For x is u was 5 root of 3, but this is squared, plus for y it is a half m times 5 squared, which is going to be, so have 5 root 3 squared is the same as 25 times 3. 25 times 3, 75. So I have 75m over 2 plus 25m over 2, which is 100m over 2, which is the same as 50m joules. So this is 50m joules and this is 50m joules. So the collision is elastic, or kinetic energy is conserved. So kinetic energy conserved, hence elastic. Kinetic energy is conserved, hence the collision is elastic. Okay. Let's now talk about the final part, which may not be common in the exams, but is called a ballistic pendulum. So a ballistic pendulum is a device which is normally used by people who manufacture, say, guns to determine or to measure the speed of a bullet. It is normally used by people who manufacture guns in order to estimate or to be able to determine the speed of a bullet. The speed of the bullet that is during manufacturing. So a ballistic pendulum may look something like this. It has a firing point where the bullet is going to be placed, and there's a material in which the bullet could embed so that it is moved through a certain angle, which angle can be measured from the scale. And if we can measure that angle, then we can be able to determine the speed of the bullet, as we are going to see. So a ballistic pendulum is a device which is used to measure the speed of the bullet. So let's think of a situation where we have a bullet. Suppose the composite body or a bullet has been fired into a wooden block, such as this one here, and the composite body has a bullet and a block. When the bullet hits the block, assuming the block is displaced through an angle, which angle is represented by theta, remember that angle is measured from the pendulum, the ballistic pendulum, using a scale which measures the angles. So suppose the composite body moves with a velocity v after collision, and given that the composite body comes to rest a height h above the original position of the wooden block. So here we are going to conserve momentum. Before the collision, it is the bullet alone which was moving, so the momentum before is going to be m times u, the other one is 0. Then after collision, it becomes one body whose mass is capital M plus m, and the velocity becomes one velocity, which is v. So that means if we consider conservation of momentum, we have that mu plus m0, m times 0 is equal to m plus capital M times v. So we can get the initial velocity of the bullet to be equal to capital small m plus capital M over small m times the composite velocity. But then if we consider conservation of energy, just after the collision, so if we consider conservation of energy just after the collision, the kinetic energy just after collision is converted into gravitational potential energy, or it is equal to an increase in the gravitational potential energy when the composite body rises to a certain height or through a vertical height h. So the kinetic energy just after the collision is equal to a half times total mass times the speed just after the collision, which is v, which becomes gravitational potential energy m plus, which is lost to become gravitational potential energy, which is capital M plus small m times gh. And when you make v squared the subject, you can find out that v squared is equal to 2gh. So the speed of the composite system can just be obtained from multiplying or from the square root of 2 times acceleration of free fall times the vertical height. So if we can measure the vertical height, or we can calculate the vertical height, then we can find the speed with which the composite object moves. Let's see this in an example then. A bullet of mass 10 grams, traveling horizontally at 100 meters per second embeds itself in a block of mass 990 grams suspended by a string of length 2 meters so that it can swing vertically. Find the vertical height through which the block can rise, the angle through which it is displaced. Okay, so just to sketch this, because although many times the sketch is not very necessary because it is always given. So let this be the initial position of the block, and let's say this is the final position of the block. And let's say it has moved through a vertical distance height, a vertical height h, through an angle, call it theta, and here the bullet has been embedded into the block. The bullet was initially moving on its own. So we have 10 grams for the bullet at 100 meters per second, embeds itself in the block, 990 grams suspended by a string of length 2 meters. So the L is 2 meters. So that it swings vertically. Find the vertical height. Find the vertical height through which the block can rise. Okay. So to begin with, we can use conservation of momentum. For the initial, it is only the bullet which is moving. So total momentum, I will not change the units because I know when I equate both sides in grams, the units will cancel out. Before collision, total momentum is going to be 10 times 10 grams times the speed, which is 100. I'm using momentum equals to mass times velocity. 10 grams times 100 plus the block was at rest, so momentum is 0. After collision, it becomes 1 mass, which is 10 plus 990, which becomes 1000 grams times the velocity with which the system moves, which I'm going to call v. So grams has cancelled out, so it means v is going to be equal to 1 meter per second. So grams cancelled out. V is going to be 1 meter per second. That is the velocity with which the system moves initially when the bullet hits the wooden block. Okay. Then So it means we are now going to use, this was conservation of momentum. Then we are going to conserve kinetic energy. The initial kinetic energy immediately the bullet hits the wooden block is going to become gravitational potential energy. So I will say loss in kinetic energy becomes gain in gravitational potential energy. So we shall have a half times the mass, which is of course 10 plus 990, that is 1 kilogram, times the speed, which is 1 squared, should now become the gain in gravitational potential energy, which is the mass, which is 1 kilogram, times g, which is 9.81, times the height h. I'm saying I'm considering a half into small m plus capital M times v squared is equal to m plus capital M times gh. Of course, this one cancels with that anyway. So we remain with the fact that h is equal to this one is the same as this. So h is going to be equal to 0.5 divided by 9.81. So I'll just press my calculator. 0.5 divided by 9.81. So h is going to be 0.051 meters. So h is going to be approximately 0.051 meters. Then the angle through which it is displaced. So if h is 0.051 meters, then I can use a simple triangle here. So I have the vertical here, I have this line here, and then I have this. Remember, the whole of this length here is the same as the other length. But this height alone is 0.051 because the block is here. So it means this was 2 meters. So this is 2 meters minus 0.051. So this becomes 2 minus 0.051. The angle here is theta. So I want to find the adjacent. 2 minus 0.051. This is 1.95 meters, or 1.49 meters anyway. So adjacent hypotenuse, that is cos. So I have that cos theta is equal to 1.95 divided by 2. Adjacent hypotenuse, that is cos. So what is theta? Theta is going to be the cos inverse, 1.95 divided by 2. Then I get the cos inverse of the answer, which is 12.8. Theta is about 12.8 degrees. If you're doing Cambridge, you may not find such questions there, but if you're doing advanced, more advanced, maybe AQ or OCR, you may find such questions. Okay, a bullet of mass 20 grams traveling horizontal at a speed of 200 meters per second and made since off in a block of mass 990 grams suspended by a string such that it swings freely. Find the vertical height through which the block rises. So I've done almost the same thing. By conservation of momentum, total momentum before collision is going to be 20 grams times the speed, which is 200. The other one is at rest, so I'll say plus 0. When they collide, it becomes one body whose mass is 980 plus 20, that is 1000 grams, times the speed, which is not known, v. So this means the v is going to be equal to 20 times, so this is 4000 grams divided by 1000. So it means v is going to be 4 meters per second. I say the grams cancels out, that's why I'm not converting. So that is the velocity with which the combined system moves. Then we say the loss in kinetic energy when the system just starts moving becomes the gain in gravitational potential energy. Therefore, a half into m plus capital M times the combined velocity becomes m plus capital M. That is the combined mass times g times h. So this one is cancelling out. In other words, h is going to be 0.5 for a half times v squared, which is 4 squared, divided by g, which is 9.81. So this gives you 0.5 times 4 squared divided by 9.81, which gives you about 0.82 meters. So that is about 0.82 meters as the vertical height. You can try to find the difference in kinetic energy, or how much of the bullet's energy becomes heat or becomes kinetic energy, and so on and so forth. Okay. A bullet of mass 40 grams is fired from a gun 200 meters per second at 200 meters per second and hits a block of wood of mass 2 kilograms. So the mass of the block is 2 kilograms. In the wooden block. If the bullet gets embedded in the wooden block, calculate the maximum angle the string makes with the vertical. The maximum angle the string makes with the vertical, state a factor. State a factor which the angle of the string depends. So if you have seen the first example, you should be able to solve this. I will not solve this. I'll just give a simple or short hint. I'll just calculate using my calculator the answer which I expect you to get, so that you try and follow the first example to be able to solve this. So you must consider conservation of momentum to find the velocity, the composite velocity, composite initial velocity. Then you can use conservation of kinetic energy to find the vertical height. Then you can subtract the vertical height from the length of the string, and then use the cosine. Cos of theta is equal to adjacent over the hypotenuse, which gives me theta as, I expect you to get theta as 52.4 degrees. You can try that. Which factors does the angle of swing depend? Of course, the angle of swing is depending on the speed of the bullet, because the speed of the bullet is determining edge, and it is also depending on the length of the string, because we are getting cos theta from adjacent, which adjacent is the length of the string minus vertical height h, then over the hypotenuse, which hypotenuse is the length of the string. So it is depending on the length of the string and the speed of the bullet, because the speed of the bullet is determining h. So the angle is dependent on those factors. But I said, if you're doing Cambridge, you may not find details of such questions in your exams. Okay, so finally I have given a self-check, which is just a reflection of what we have just been covering all along. You can always pause the video and start practicing. A board of mass 20 kilograms moves with a uniform velocity of 4 meters per second. Calculate the momentum. Remember, always write the formula. Momentum is mass times velocity, and then you substitute. An object of mass 2 kilograms moving at 5 meters per second collides with another object of 3 kilograms, which is at rest. That means here velocity is 0. Find the velocity of the two bodies if they stick together after collision. We have done such an example. Total momentum before collision should be equal to total momentum after collision, but if they stick together, it becomes one mass, which will be 3 plus 2. You should be able to get that answer. A board of mass 20 kilograms moving with a uniform acceleration has an initial momentum of 2000 kilogram meters per second after 10 seconds. And after 10 seconds, the momentum is 300 kilogram meters per second. What is the acceleration of the body? So you have a change in momentum. The resultant force F is equal to mass times acceleration, which is the rate of change of momentum. So you want to find the acceleration. So I would simply say the mass, which is 20, times the acceleration is equal to change in momentum, which is going to be 300 minus 200 divided by the time, which is 10 seconds. So it means the acceleration is going to be equal to 100 divided by 20 times 10, which will be equal to 0.5, I think, meters per second squared. You can also verify that. If resultant force is mass times acceleration, but it's also the same as the rate of change of momentum. So I think it should be able to give you such an answer. You can always pause the video and try to work out before you see my hint. A moving ball P moves of mass 100 grams collides with a stationary ball Q of mass 200 grams. After collision, P moves backwards. In other words, it rebounds. So its velocity could be negative after collision with a velocity of 2 meters per second, while Q moves forwards with a velocity of 5 meters per second. Calculate the initial velocity of P. So I'll just sketch this, I will not solve it. You can pause the video, follow the sketch, and then complete this. So before collision, this is what we have. We have P and Q. So moving ball P collides with a stationary. So this one is stationary, so here velocity is 0. And this is moving. It must be moving towards Q. Its velocity is not known. Let me call it U. U is not known. This is before collision. Then after collision, P rebounds. It moves backwards with a velocity of 2 meters per second, and yet Q moves forward with a velocity of 5 meters per second. So we want to find the initial value of U. So here you just use conservation of momentum. Remember, so this is after. Always remember to assign velocities, maybe to the right positive, to the left negative. So, okay, I will solve this anyway. So total momentum before collision, remember momentum is mass times velocity. So for P, I will not change the units because I know the grams will cancel on both sides. So for P, it will be mass 100 grams times its velocity U to the right hand side plus 0 is equal to, after collision, because this is in the opposite direction, to be negative. So this will be again 100 grams times its velocity, which is 2, plus, for Q, it is to the right hand side, will be positive. Its mass is 200 grams times its velocity, which is 5. So the units grams have cancelled out. So to find U, U is simply going to be equal to 200 plus, I think this is 1000. So this is 1200 divided by 100, which is going to be equal to 12 meters per second. That's what I think. 200, oh, sorry. The other one is negative. Negative 200 plus 1000, that is 800. So this is 8. So that is 8 meters per second. So that is going to be the initial velocity for P. It is about 80 meters per second. I hope that is correct. You can check my calculation. Then part 2, so this is part 1. Then part 2, the force exerted by P on Q if the collision took 0.03 meters per second. Of course, remember, the momentum, the change in momentum of P due to Q is equal but opposite the change in momentum of Q due to P. So the force is equal to the change in momentum over time. So I'll just find change in momentum of P because it is the same, equal but opposite. For P, its initial momentum was 100 times U, which is going to be 0.1 times initial velocity, which was 8, minus after collision it is 0.1 times 2. But this is in the opposite direction, so I must put a negative minus negative. So the force is going to be equal to 0.8 plus 0.2 divided by 0.03. I said minus negative because for P, its initial momentum was to the right, and after collision, its momentum is to the left. So it is minus negative. That is the change. So 0.1 times, so 0.8 plus 0.2 divided by 0.03. So I think the force is going to be approximately 33 newtons. You can also verify. A sphere of mass 3 kilograms moving with a velocity 4 meters per second collides head-on, that means in a straight line, with a sphere of mass 2 kilograms and impacts to it a velocity of 4.5 meters per second. Capture the velocity of 3 kilogram sphere after the collision. So I think you should be able to solve this. Yeah, you should be able to solve this because the other sphere was stationary. So if I sketch this, this is sphere of mass 3 kilograms and the other one is a sphere of mass 2 kilograms. This was moving with a speed of 4 meters per second. This was at rest. So after collision, we don't know the velocity of the sphere of mass 3 kilograms, but we know the velocity of the 2 kilogram mass. Of course, with this one, we can predict that it moves in that direction, 4.5 meters per second. So what is the velocity of 3 kilograms? So you should be able to find that using conservation of momentum. A rated track of mass 4 times 10 to the power of 4 kilograms moving at the velocity of 3 meters per second collides with another of 2 times 10 to the power of 4 kilograms, which is at rest. The coupling join, so it becomes one body. So total mass becomes the sum of the two. And the tracks move off together. Capture the common velocity. So here you just use conservation of momentum. Initially one was moving, so total momentum before is 4 times 10 to the power of 4 times 3 plus 0. Then after it becomes one mass, so it is 4 times 10 to the power of 4 plus 2 times 10 to the power of 4, then times the common velocity v. You should be able to find v. And finally, a bullet of mass 12 grams is fired horizontally from a gun with a velocity of 180 meters per second. It hits and becomes embedded in a block of wood of mass 2000 grams, which is freely suspended by a long string as shown besides. So that should be shown besides. Calculate the magnitude of the momentum of the bullet just before it enters the block. So that one is mass times velocity. You can check and see if that answer is correct. The magnitude of the initial velocity of the bullet of the block and the bullet after impact. So here you just say conservation of momentum. Total momentum of the bullet becomes or should be equal to total momentum when the bullet hits the block. That means it is equal to total momentum of the combined system. Then the kinetic energy of the block and embedded bullet immediately after impact. So if I have this velocity, I just multiply this half m total mass times this velocity here squared. Then deduce the maximum height above the equilibrium position to which the block and embedded bullet rises after impact. So the loss of this kinetic energy becomes the gravitational potential energy, mgh. So you should be able to follow through the examples we have done to arrive at these answers. If you find any challenge, you can always raise a comment or you can always raise your concern. Write a comment. I'll always be able to help you. Yeah, I think dynamics should stop here. I've tried my level best to take you through the basics, and I try to go through them because I'm sure I'm teaching A-level students who must be able to understand these concepts extremely easily because they have developed minds now. Nevertheless, if there's any problem, you can always write to me. Do not forget to watch the solved past paper questions, which will give you a lot of information that you need to pass dynamics. Until next time, bye bye.